Okay, chapter 26 is on the properties of light. So anytime you shake an electrically charged object back and forth, you produce an electromagnetic wave which travels out through space in all directions, in fact. I'm just showing one particular direction here. And what I'm showing is the electric field plotted with this red line going up and down, and the magnetic field plotted with these blue lines going sideways. So the electric and magnetic fields of an electromagnetic wave are always perpendicular to each other. And they're also perpendicular to the direction that the wave moves. So this peak in the electric field strength will move along at the speed of light, as will this one. And they will go in the direction that's perpendicular to the magnetic field oscillations and the electric field oscillations. So in a vacuum, all electromagnetic waves move at the same speed. It's very, very fast, about 300,000 kilometers per second. So we classify different kinds of electromagnetic waves based on their frequency, or equivalently their wavelength. And here is a whole list of all the different names we give to the same thing, which is really these are all electromagnetic waves. Radio waves have frequencies of about 1 million hertz. Microwaves are in the billions of hertz. Then you start getting into infrared is 10 to the 13 kind of hertz. Light that we can see with our eyes is one kind of electromagnetic wave. Right in here, sort of in the 10 to the 14 hertz frequencies. Then you get out into ultraviolet, higher than that, X-rays, and the highest frequency form of electromagnetic radiation is called gamma rays. So in terms of light, the lowest frequency and therefore longest wavelength light our eyes are sensitive to appears red. As you increase the frequency from red, you go through orange, yellow, green, blue, and violet is the highest frequency light that our eyes are sensitive to. And violet has about twice the frequency of red light and about half the wavelength. So some materials are transparent, like glass. And glass, as it turns out, is transparent for frequencies of light which are visible, like our eyes are sensitive to, but it turns out that it's opaque to ultraviolet or to infrared. So for a transparent material, you have light which moves along at the speed of light, then it hits maybe an outer atom of this glass, and that energy is for a very, very short time kind of contained in that atom. Then it is quickly re-radiated to the next atom, which absorbs that energy, then radiates it to its neighboring atom, and all the way along through 10 to the 23 atoms until it comes out the other side. And because of all these little delays, as the energy is captured by all these adjacent atoms, the average speed of light through a transparent material is always less than the speed of light in a vacuum. So in a vacuum, light travels at speed c, where c equals 300 million meters per second. In air, the speed of light is slightly less than c, but we usually round it off to about c, 1.00 or 0.999. So in water, the speed of light is 0.75, about 3/4 of c. And one of the interesting things about changing the speed at an interface is that it also changes the direction of light waves a little bit. So when you look through a transparent material, you'll often see light bending or refracting, like you do with a spoon in a cup. Glass, about 2/3 of c, and in a diamond, light travels at speed 41% the speed of light, which is which makes the light bend a lot in a diamond, and it makes it look very sparkly or pretty. Most things around us are not transparent, they are opaque, which means that they absorb light without re-emitting it. So when light hits a opaque material like a book or a house or a brick or something, the vibrations given by the light get absorbed by the atoms and turned into random kinetic energy, so thermal energy. Here you can see sunlight hitting a roof and warming it up a little bit. But in this shadow area where a tree has blocked the light, the roof is colder, and you can see it's still frosty from frost that was there in the morning. Metals are opaque, but the light shining on a metal immediately forces free electrons to vibrate and re-emit that light as a reflection. So if the surface is very smooth, you can see reflected light in a metal, like this guy's face. So light, when it travels through a vacuum or through the air, travels along straight lines called rays. And so if there is an opaque object, these rays will form a sharp shadow, especially if they're coming from a very distant or very small source. If you have a larger source of light, you can end up with a kind of a blurry shadow. And so here we see the sun and the moon and the earth. And this gives a good example of a blurry shadow, where the very center part of the shadow is where the light from every part of the sun is blocked by the moon, and that is called the umbra. It's a total shadow. But in this region around the umbra, it's called the penumbra, there's parts of the sun that are blocked by the moon, and other parts of the sun that have rays that can just reach those places. So it's a sort of a lighter part of the shadow. So while we're on the subject of eclipses, there's two kinds of eclipses. A lunar eclipse, where people on the Earth see first a full moon, and then the full moon falls into the shadow of the Earth, and the moon looks dark. And there's also a solar eclipse, and that's where there's a new moon, which you can't really see from the nighttime side, so you have to be standing over here on the daytime side of the Earth. When a new moon moves in between the sun and the Earth, a shadow of the moon can fall on the surface of the Earth, blocking the sun. So observers here in this shadow will see a solar eclipse. The eye, one of the most remarkable optical instruments ever known. So as light enters the eye, it moves through a transparent cover called the cornea, which does about 70% of the necessary bending of light before it passes through an opening in the iris, which is this colored part of the eye, and the opening is called the pupil. The light then reaches this crystalline lens, which fine-tunes the focusing of light, that then passes through a gelatinous fluid called the vitreous humor. It eventually ends up on the retina, which covers the back sort of 2/3 of the eye, and that's responsible for this wide field of vision that we can experience, or peripheral vision. And in order for our vision to be clear, light must be focused. If it's all coming from the same direction, it must be focused right on to the retina. Now the retina itself is not uniform. In the middle is the fovea, which is a region of distinct vision, a lot of little light-sensitive cells there. And behind this whole retina, there's an optic nerve, and there's a spot in the retina where the optic nerve is connected, and that forms a blind spot where we can't actually see, but it's not in our fovea, so we don't often notice our blind spot. And this is just a microscopic image of a retina, showing that it's an array of little tiny antennae that resonate to the incoming light and are connected to nerves, which go to our brain. And there's two kinds of antenna. The rods handle vision in low light, and there's a lot of them around the periphery of the retina, where our peripheral vision comes from. And the cones, these larger cells, handle color vision and detail, and they're much more dense in the fovea. And there's actually three kinds of cones, which handle low, intermediate, and high frequencies of light, corresponding to red, green, and blue. And that's how we have our color vision.